Keys up, scores are posted. Number of folks did pretty well. Number of folks didn't. But for those who didn't do very well, keep in mind, all kinds of earnable credit available on coming quizzes and exams. You have ample time to elevate your level of achievement to whatever extent you would like it to be elevated to, provided you do what's necessary to produce the elevation. Special Quiz 1 is almost developed. I was working on it yesterday. I expect to publish it today. If not today, tomorrow at the latest. If you've looked at past special quizzes, which were until now labeled bonus quizzes, same thing. But I decided the bonus quiz label wasn't quite appropriate because it really is part of the earnable grade points for the course. So I changed it to special quiz. So what? You will see, this is stated at the top of bonus special quiz 1. You can use any source of information you want. Each other, work in teams, Google, notes, you name it. In fact, it's common practice for some of the questions I ask you, you're going to have to go to Google. Unless, for example, for this special quiz, you happen to know straight away the structure for carnosine. Everybody know that? I didn't think so. Alanine histidine, an important amino acid. You ever hear about amino acids? You think they're important? Any of you might have an interest in the future in biochemistry. Guess what? This is the kind of stuff you need to know. And it all follows from the stuff we are doing. You'll learn about things like isoelectric point, how to apply Bronsted-Lowry acid-base equilibrium analysis to this alanine histidine system in order to answer the questions which I shall pose to you on this special quiz. It all follows from what we're doing. And will enrich your knowledge and vocabulary of chemistry. I think the due date is something like 3 weeks from tomorrow. Time is not my concern. Your achievement and the development of your knowledge and understanding of chemistry, that's what I want. So I don't put any time limit of consequence on these things. Oh yeah, and any source of information, work with each other as you wish. But let me remind you, if you work with each other and somebody generates the special quiz of the group with whom you work, and all you do is copy it, you're getting nothing from this, nothing. You do not learn by osmosis. By copying answers from an answer key or somebody else's paper. Understanding does not creep up through your pen or pencil, through your arm and into your noggin. Because I think by now you know when you get an in-class quiz or exam, you have to understand. That's what it's based on. I will never ask a question which is simply a repeat of something I've told you in class. I don't give a damn about Jeopardy. That's not what this is about. When people get a lot of money for reciting facts that anybody can look up in an encyclopedia, I object. Understanding is where it's at. Not recitation of encyclopedic information. Because that in and of itself shows no understanding or comprehension of the subject at all. And you're not going any place in science. You're not going any place in any real position of consequence without understanding, without the ability to think and analyze problems. That's what this is about. And that's what we aim at. And that's why this class is hard as hell. But so what? That's what real education is premised on. Now, of course, there's one limitation on the help that you can receive on working with special quizzes. No professional chemistry instructional help. That's against the rules. If you come to myself or the TAs for our gathering, we'll explain something to you if it's a matter of you don't understand what the question is asking. But under no circumstances will we provide you with any information which will direct you how to solve the problem. That's your responsibility. That's the rules of the road for a special quiz. Bunch of points will be earnable. I haven't finished writing it yet, so I don't know. For exam 1, you'll recognize from your scores that I assigned 13 points for each correct answer. Hey, that computes to a hell of a lot more points than the 200-point base value which you see in the syllabus for the exams. And the TAs received some questions about, what about these points I see in sockeye? That means nothing. I have to live with that dumb program. I have to invent ways to outwit it because it insists on determining grades based on percentages, which I abhor. Total points is all that matters. So you add up the points you've earned. Don't pay attention to any of this point information that you see at the top of a quiz or exam column in sockeye. That means nothing. That's just a game I played to fool that damn thing. I had to put a bunch of points in there which are far beyond what you can earn on any quiz or exam because I found out that if I've placed a 100-point value for a quiz, and you know how I write the quizzes. Some of you made over 100 on the first quiz. Good for you. Well, I found out this damn dumb system, if you put in a value that's over this earnable value that you put in there, won't accept it. Damn this dumb thing. All I wanted to do is add points, and it won't do it. It'll give me all kinds of ways to invent all kinds of fancy quizzes where I can throw away quiz question 3 and question 5 and give half credit for question 7. I can do all that junk, but this idiot program cannot add points and compute a grade accordingly. And I've screamed and hollered and raged at the people that run this for 4 years. What have they done about it? Not a damn thing. They invent more bells and whistles. I said, I got 2,600 lab grades to do this term, and another 150 or so for you folks. Where's my consideration? There's nobody in this university that comes close to having to submit as many student grades per calendar year as I do. I'm way ahead of everybody. Where's my consideration? That's where it is. And I resent that. And I want the matrons of the world to know this, damn it! Oh well, now I feel better, and so we proceed. But in any case, please don't ask any more questions regarding grades on the basis of out of. Out of means nothing. There's no out ofs, there are no percentages, just total points, nothing else counts. But again, I'm sympathetic with you folks, not in the least angry. It's the system controllers with whom I have to gripe. Okay. Now we come to the real fun aspect of hydronium ion concentration determination, calculation, if you will, for water solutions of polyprotic acids. Now with the specific acid type being a hydrated metal ion. Why is this the most fun case? Well, to review in brief. We looked at the parent molecular acid, a parent acid being molecular and strong, sulfuric. First ionization, 100% extent. So second ionization involves the equilibrium upon which you have to do arithmetic to get the hydronium ion molarity. Parent acid, polyprotic, molecular but weak. like hydrated CO2 or H2S or a bunch of other acids you see in our acid-base table. Hydronium ion concentration, simple. Why? Because you need only pay attention to the first ionization. Second ionization relative to the first ionization will always, practically speaking, go no place. As brought to our attention by the fact that Ka2, when the parent acid is weak and molecular, Ka2 is going to be a real tiny number next to Ka1. We even did a proof to show you why Ka2 cannot contribute. Aha! But now we come to the one I like the most, because it's the most challenging. And that means from this you will likely learn the most. That's the best part of it. The hydrated metal ion. A hydrated metal ion solution which is fairly dilute. You know what the impact of the dilution is? You remember that on ionization extent? The more dilute, the greater the ionization extent. Remember that? So, we're going to have to recognize what the principal system inventory is for this solution after we look at some information. First, to get at the information, I've made these notations so I can write these equilibrium reactions without writing these long formulas over and over and over again. And other reaction equations, and other equations we're going to write here in a moment. This stuff, if you get a bottle of iron nitrate, you know, a laboratory reagent bottle, ferric nitrate, and open it up, you'll see it's a nice pale violet. A gemstone has a color that resembles this. I forget what it is. Topaz, I think. Maybe that's not right. Okay? So first concern would be, if I make this solution, do you think the solution will show me a pale violet color? Well, let's look at some more information. This stuff is yellow-brown, as is this stuff. How do you think the intensity of yellow-brown compares to pale violet? If I mix equal mole quantities of pale violet and yellow-brown, what color do you think I'll see? Yellow-brown. Pale violet's not very intense at all. So with that, let's look at these two ionization equilibria, which correspond to Ka1 and Ka2 respectively for quote-unquote Fe3+. And then we'll wrestle with questions 1855 about Ka1 compared to Ka2, and 1856 about the color of this solution. Here's Ka1. The value is 4.0 times 10 to minus 3. You've already recognized, I believe, as far as weak acids are concerned, that's a pretty large Ka value. It's a Ka value that's a hell of a lot bigger than 10 to minus 7. So you know, under conditions of fairly extreme dilution, this thing can go 100%. Now let's look at Ka2. 5.0 times 10 to minus 4. My golly. Remember the weak polyprotic molecular acid? The difference between Ka1 and Ka2, for example, for H2S, was 1 trillion. What's the difference here? 8. This thing is 8 times bigger than this. What's that mean? You think in this case we got to consider the second ionization equilibrium as well as the first to correctly compute the hydronium ion concentration? You're damn right. And that's why this is a much more challenging problem. Because guess what? As things stand, we got 2 equations. There they are. But how many unknowns do we now have? Because we got to consider both of these. So after we make this solution, we won't know the molarity of this. We won't know the molarity of this. That's what we want. We won't know the molarity of this, and we won't know the molarity of that. That's 4 unknowns. You got 2 equations. Can you solve it? No. So what do we have to do? You learn this in algebra class. If you've got a system composed of 4 unknowns, you need 4 simultaneous independent equations, at least 4, composed of these same 4 unknowns. So in order to crack this puzzle, we got to write 2 more equations. And we shall in a moment. Now, Why do you think Ka2 is only a little bit smaller than Ka1 when this weak polyprotic acid is a hydrated metal ion, not a molecule? Come on, Coulomb, what do you got to say about this? Now remember, this abbreviational reference is really this thing. Okay? Got a charge of +3. When this loses H+, it reduces to a charge of +2. So something that's +3 reacts to lose H+ and converts to something that's +2. Do you think that's a coulombically favored process? Because it involves charge density reduction by bringing about, or as a consequence of, separation of like charged particles, right? H+ is going away from this quote-unquote iron +3. Is that coulombically favorable? You're damn right, because like charged things repel each other. And that applies to the second ionization equilibrium as well. So these equilibrium reactions are each coulombically favored, as opposed to what we looked at with the molecular acid, where after the first ionization you're pulling H+ away from something that's minus. That's coulombically unfavored. These are coulombically favored. That accounts for why there isn't much difference between Ka1 and Ka2. So, back to the color. This is not a large concentration at all. So before we do any arithmetic, we can well expect that the ionization extent of this first equilibrium reaction, as well as the second equilibrium reaction, before equilibrium is achieved, pretty large. Okay? So what do you think the color is of this solution? It's going to be yellow-brown. You're in fact going to do some chemistry with this stuff when you get to assignment 10 in 46L, and most of you will get there. As the syllabus for 46L tells you, whatever work you do that's acceptable in assignments 10 and 11, if you get there, is simply added to your total points. Because lab scoring is just like scoring for our lecture class. Never mind the rigmarole, I have to go through the full Sakai. Total points is all that matters. 46L says when you've amassed 900 points or more, you've made an A, and many students will make an A before the final, because they will have earned more than 900 points as a consequence of quality laboratory work. Yet some of these students will come to me and say, I have over 900 points, but do I have to take the final? What do you think I tell them? I tell them, you're damn right. If they don't believe the syllabus, what should I mean, hey, so take the final. If you make a 0, you still made the A. But it's a learning experience. And if you don't believe me after I've told you in the syllabus what you made 900 more, you made an A, you say, do I have to take the final? I say, of course. But keep this in mind. You don't have to take any exam in the university. None. If you like zeros, if you like to fail, you like to get thrown out, that's your prerogative. I hope you don't exercise that prerogative, but it's your prerogative. Nobody holds a gun to you and says, you have to take this exam. Never. And I'd never run a university like that. I want you to decide. Are you here because you want to be? If you are, I'm for it. But if you don't want to be here, I'd just soon you go away. I mean it. Let's clear the path, get the clutter away, so as to not disrupt the progress for those of us who want to be here. But I'm going to be a believer that you all want to be here. And so, we proceed with the challenge of developing the other equations that we must have to solve this puzzle. How many unknowns? 4. After these two equilibrium reactions and no others. So how can we get the hydronium ion concentration? We got to consider this, which we've already talked about. Remember what this is? Material balance and charge balance. That's the part of the puzzle we've told you we're going to have to look at, but as yet haven't looked at it. Now we look at it. Now it's official. Here's material balance for the iron stuff that's in solution. It's simply the sum of the equilibrium molarities for each form of iron that's in solution. And that's equal to 0.010. Because that's how many moles of iron was dissolved per liter of solution to make this solution. And now charge balance. The part of the puzzle which, before this moment, we have yet to look at. It's based on the principle of electroneutrality. I told you this before. You can't go to the lab and get a bottle that's only got positive ions in it or conversely negative ions. That's impossible. Such a system is horribly unstable. Each bulk chemical system, if it is to be stable, each bulk chemical system has got to be electrically neutral. It's got to correspond to charge balance. What does that mean? That means if for a system which contains charged particles, and every water solution contains charged particles, the sum total moles of positive charge has got to be exactly equal to the sum total moles of negative charge. No more, no less. With that consideration, we can write this remaining reaction equation which we need to solve this puzzle. Now then, before we write the charge balance equation for our iron nitrate solution, let's take a look at a simple case so you can see, or I hope you will see, that writing charge balance equations is an easy task. It's not difficult at all, provided you have already done what for the system? Written what? How about that? If you got the PSI, you got it. And if you don't have the PSI, it's got you. 1 molar calcium chloride solution. Let's write the charge balance equation for this solution for principal species. Now then, in this solution, tell me right now, what are the principal species? And I'll write them down. What is that? Calcium ion. What else? Chloride ion. What else? Water. That's it. Now I'm writing a charge balance equation. Do we include water? Has it got a charge? No. So water or any molecular species is never included in a charge balance equation. Only charged particles, ions, that's it. Now then, we know for this solution that the molarity of calcium ion is, and the molarity of chloride ion is, what is it? 2. Really hard. Really hard, this one, wasn't it? So, if I want to equate positive charge, moles thereof, to negative charge, moles thereof, what do I have to do to the molarity of calcium ion to set it equal to the molarity of chloride ion? What do I have to do? What do I have to do? What do I have to do to this molarity to set it equal to this molarity? Double it, don't I? 2 times 1 is 2. Wow, that's tough. So here we go. There's the charge balance equation. What could be simpler? So keep in mind, what this has shown us is that to write a charge balance equation, which means again, you're going to write an equation which establishes an equivalence between total moles of plus charge with total moles of minus charge. Okay? So we're going to write down the formulas for all the positive ions. Wrap square brackets around because we want molar concentrations. Write down the formulas for all the negative ions. Wrap square brackets around because we want molar concentrations. And do what to each concentration as a function of ion charge magnitude. What are we going to do to each species concentration, each ion concentration, as a function of ion charge magnitude. We're going to multiply that concentration by the ion charge magnitude. Do you see what we did here? The charge on calcium ion is 2, isn't it? From a magnitude standpoint. So to write this equation, I had to take the calcium ion molarity and multiply it by 2. That's it. The chloride ion molarity is multiplied by 1. Well, I'm not going to write that down. That's implicit in writing the chloride ion molarity. And then, if it's possible, we will set this charge balance equation to a number. This number has a name. Let's get this out of here. It's called charge sum. We will see that in many cases, after having written a charge balance equation for a system containing ions, we can write the charge sum value as well. That just gives us more information with which to work. But sometimes we will see we can't write the charge sum. Not straight away. That's a more challenging situation. We'll take a look at examples so that you will become aware of the specifics of when you can set the charge balance equation equal to a charge sum and when you cannot set the charge balance equation equal to a charge sum. All right? Now then, you've seen enough. If you paid attention to what we said, you can do this. Let's write the charge balance equation for all the species in the iron nitrate solution. And you will also see in writing this why we have to do this for all the species in order to tackle the problem which we have set forth to tackle. Have we got all the positive ions? Now let's get at the negative ions. You see any other negative ions in this system? With your chemical eye, not what I've written on the board. Because really, a lot of what we've done this term is to program you with a chemical eye that allows you to look into a solution and see what's there. Because these buggers which are in that solution cannot be seen with the naked eye. Cannot be seen with any magnifying device of which I am aware. And just because this is water in my cup, which means it's got hydronium ion and hydroxide in it, no matter how intensely I may stare at this solution, no matter how long I may stare at this water solution in my cup, the hydronium ions don't look up at me and say, I'm hydronium ion and I am here. You have to know that as a consequence of your developing knowledge of chemistry. And now you know that stuff. Okay? And after this, we'll write equals charge sum question mark. In other words, we're saying we don't know yet if we can set this one equal to a charge sum. I'll give you a hint. We can. Now then, remember what we said? To write this charge balance equation, you write the formulas for all the positive ions. We did that. Wrap square brackets around because you're going to write this in terms of molar concentration. We did that. Formula for all the negative ions, wrap the square brackets around. We did that. And then you examine each ion so that you can take the concentration for that ion and multiply it by its charge magnitude. That's all you have to do. And here we've shown you why. So I multiply this by done. There's the charge balance equation, chemically speaking. That's all there is to it. I told you this is easy to do. Now the charge sum. Statement. Yes, for this system we can write the charge sum. What is it? You tell me, and I'll write it on the board. I'm listening.
0.03.
0.030. Don't forget the significant figures, but thank you for the 0.03. You believe this? You see that bottle label? Up there? What's the nitrate ion molarity in this system? It's 0.030, isn't it? Does the nitrate ion react in any fashion from an acid-base standpoint in this system, even though it's in there? Does it? No. So the nitrate ion molarity is 0.030. Now, is this system acidic or basic? It's acidic. So what do you know about the molarity of this? It's got to be smaller than 1 times 10 to minus 7. If I had a number that's smaller than 1 times 10 to minus 7 to 0.030, am I going to make 0.030 change? No. So I can strike this. If I need it, I can put it back. And if I need this in terms of hydronium ion concentration, what can I do? Can I write this? Yeah. Now that's not another unknown. Okay? Now then, this is what we're looking for. We do not know yet, although we got a pretty good idea, if this is or is not a principal species in this system. Now, if we are assigned the task of computing the hydronium ion concentration for any water solution, we got to have the hydronium ion in there someplace. So it better be part of the charge balance equation, even though it may not be a principal species. That's why I asked you to write this for all species. Do you think for this case the hydronium ion is a principal species? You think the ionization extents of these reactions are substantial? The K values, as far as weak acids are concerned, are pretty large. They're a hell of a lot bigger than 10 to the minus 7, and the dilution is great. Well, not great, but it's fairly substantial. It's only 100th molar. So you can bet the hydronium ion molarity is substantial in this system. Okay? And now we got what we need. Because we've now written an equation, which in addition to the equations we previously had, gives us our fourth equation, composed of the same four unknowns. So we can solve. What do we do with the material balance equation? We take any one of these forms of iron and solve for it in terms of the other two. Right? Nothing fancy about this. I write this molarity is equal to 0.010 less this molarity less this molarity, if I want to do that. Or I write this molarity equals 0.01 less this molarity less, who cares? Whatever I want. It's there. Use it as I need it. But now you see how to do it. Now tell me, if you were required to solve this puzzle, how would you proceed to solve? Would you speculate on ionization extents? Is that what we've done before? That's what we've done before, hasn't it? Is that what we should do now? You're damn right! That's the way to do it. Because we know when we get the right molarities for each component of this system, this added to this added to this will equal this. And 3 times this plus 2 times this plus this plus this will equal this. And the equilibrium constant for the first reaction will be satisfied. Because the molarity of hydronium ion times Fe2 plus, quote unquote, divided by the equilibrium molarity of Fe3 plus, quote unquote, will be 4.0 times 10 to minus 3. And the same for the second ionization equilibrium. Well, we're just telling you what considerations you would make if in fact you set about the business of solving this. We'll have more to say about this shortly. Now then, just to be sure you're on top of this charge balance stuff, I want to take a look at one more consideration that's in the notes. That's question 1857. For 1857, we're going to write Cb. What's the molarity? There's a 10th molar. Okay. Aluminum sulfate solution. First, for principal species. Second, for all species. Do you recognize from the information we've already brought to your attention in chapter 18 that aluminum ion is +3 like iron +3? It is a metal ion with a substantial positive charge density and therefore forms a well-defined hydrate. And what do we know from an acid-base standpoint about these metal ions which form well-defined hydrates? They are Bronsted acids, aren't they? Weak Bronsted acids, but nevertheless Bronsted acids whose ability to ionize is observable in water solution. So bear in mind, if you go to the lab with this solution, if you go to the lab with this iron nitrate solution, and do some simple indicator analysis, you will find that each of these solutions is distinctly acidic. And if you are a student of chemistry who hasn't learned about metal ions with positive charge densities forming defined hydrates which can behave as Bronsted acids, you'll look at a solution like this and you'll say, how the hell am I getting hydronium ion produced in this solution? Because it's got this in it and this in it. That's what happens if you're ignorant about this. But you know this isn't what you have in here, is it? This is what you have in here. At least for starters. And that's what accounts for the generation of hydronium ion. Hey. This is another something which I don't see the general chemistry books dealing with at all. I mean, how the hell do they expect you to get on with this stuff if they keep on taking this kind of stuff, the challenging stuff, and sweeping it under the rug, which to you suggests it doesn't exist? You wouldn't know about this stuff unless I tell you about it. Or somebody else who wants you to learn this stuff tells you about it. So you have been told. Okay? Now let's get on with the assignment. Principal species, charge balance for this system. Write it on your paper right now. And after you write this equation, I want you to ask yourself, can I set this equal to a charge sum? And if so, what is that charge sum? I'll give you a hint, you're damn right you can set it equal to a charge sum. Now, to assist you in what you are writing down, notice that this solution is 10 times more concentrated than that solution. Right? And also notice, this is from the acid-base table, that Ka1 for hydrate aluminum ion is 1.4 times 10 to the minus 5. And that's a whole lot smaller than 4.0 times 10 to the minus 3. I repeat, this solution is 10 times more concentrated than that solution. And Ka1 for hydrate aluminum ion is a whole lot smaller than Ka1 for hydrated iron plus 3. What does that tell you about principal species in that solution? You think it's a good bet that it's just hydrate aluminum ion? That's a good bet. So for principal species, we're going to write this. Based on the considerations we've made, we expect that the only positive ion in here of consequence, of large concentration, is hydrate aluminum ion itself. And I think it's fair to say, or I hope it's fair to say, that you all recognize that the only negative ion in this solution of consequence is sulfate ion. All right? Now let's develop the equation. What's our multiplier? Multiplier. Charge sum. Wrong. What is it? I didn't hear.
0.60.
Louder.
0.60.
Yes, that's it. Did you all hear that? How many of you are mystified by this number? You see that solution? In this solution, what is the aluminum ion molarity? 0.2, isn't it? What's 3 times 0.2? Boy, is that tough! What's the sulfate ion molarity in this solution? 0.30, isn't it? What's 2 times 0.30? Come on now. Let this stuff talk to you. It's not difficult. But I understand that it's something you've not done before. It's the newness of this which throws you off. It's like in Chemistry 2045. When we have you deal with the density equation. D density is M mass over V volume. Everybody's at ease because you've all done that in probably high school physics class or something. Nothing to it. And then you go to Planck stuff. And look at E equals H nu. Right? And most students say, ah! Not even recognizing that E equals H nu is a simpler equation than the density equation. You know why? Because in E equals H nu, H is a constant. It doesn't change. It's even an easier equation. But E energy, oh, what's that? And then nu, which looks like a V with a broken right leg. You all say, ah! And you say, ah, because you haven't seen it before. That's the only reason why you say, ah. That's why. Maybe I told you this story before. You know, I like stories. When I was in high school, and I took first year algebra, my class got an algebra quiz from the teacher, extracted straight from the textbook. All the unknowns were represented by X and Y. We did good. She gave the next class, which until that time had been outperforming us, the next class. Because you know in high school, teachers got a whole bunch of different classes, okay? The next class, she gave them exactly the same quiz, except she changed every X to an A and every Y to a B. That's all she did. They flunked. She was aghast at this, but she had read about it in a psychology article or something. She says, what the hell happened? She didn't say that. I mean, if I taught the class, that's what I'd say. What happened? You know what they told her? We know X and Y. We don't know A and B. Hey, that's it. You see something new and you go, back. It's a natural human reaction. Don't do it. Okay? And now what I want you to do with this before we meet next time is to write the all species charge balance equation for this one. And we'll take it from there.